Okay, so for problem like number one, we want to decide, can we do power rule or can we expand? And the big giveaway is the fact that there are more than one term in the denominator. Okay, whenever there's more than one term in the denominator, we're kind of stuck. Okay, a flip side would be something like this. If I had the integral of 9 minus 7x squared over 2x, then we can separate each of the fractions and we can move forward and we can just rely on moving terms without doing anything more complex. But if we have more than one term in the denominator, then we're stuck. Okay, you guys see that distinction there? Okay. So the next step is we know it has to be a U-substitution problem. Okay, has to be we have to identify a U value to allow this to work. So a good place to start looking for the U value is the denominator space. Okay, so denominator space is a good place to look. If the anything with a higher degree exponent is also a good place to start. Okay, so we'll let the U value be the 9 minus 7x squared, and we're going to try to cancel the dx out. And the hope is that if we let this be the U value, maybe we can get this to look like this rule here. This 1 over u du. Okay. All right, so we let the U value be 9 minus 7x squared. All right, Bree, so what's the derivative here?
Would it be 14x?
Okay, close. Missing one little thing.
The negative?
Yeah, the negative goes along with it. Okay.
Okay.
Okay, cross multiply. And then we want to solve for dx. Okay, all right, so Emily, what would this look like after I put this all back? If I replace those things.
Would it be 2x over 9 minus 7x squared du over negative 14x?
Okay, but we can also replace this with what?
Oh, the dx as well?
Well, the 9 minus 7x squared, I can replace this with u, right?
Okay.
Yeah, so that's our goal. I like to underline these parts to begin with because I know that these are the first two things that are going to get substituted. Okay, 2x is going to stay, but we're hoping that this x is going to move out of the way. But this is our eventual goal. Our eventual goal is we want everything to transfer to be in terms of u. So these are the first two pieces to go. Okay. All right, Emily, what happens here?
You combine them together.
Okay, and what goes away?
Do
you see?
Can you cancel out the x?
Yeah,
and
the x is canceled out.
Can you cancel out the u too?
Not the u. The u and du are separate things. These are part of the notation that we need. So we want it to look like this, right? We don't want those to go away.
Okay.
But what can I do with the 2 and negative 14?
Simplify.
What does that simplify down to be?
negative 1/7.
Yep, and we're going to push it out front. Okay, so if we push it out front, like you said, negative 1 over 7, and that leaves us with what inside? What's left inside here?
Du over u.
Du over u, which is the same thing as 1 over u du. Okay, you can write du over u or 1 over u du, but they mean the same thing. And if you look, you know that you're ready for an integral rule if you have a perfect match. Okay, once you cover up the coefficients, there should be a perfect match. And once there's a perfect match, then you're in the clear because you just follow what the rule says. Okay. So -1/7 natural log absolute value of u plus c. And is there one final thing we can do?
Plug in u.
Yeah, replace u with x, right? So we started with x, we need to end with x. Okay. All right. Any questions with number 1?
Not so far.
Okay. All right, number 2. Again, I'm looking at this going, can I expand? Can I move anything around? But I have more than one term in the denominator, so I'm kind of stuck. But if I try to go through U-substitution, nothing is going to allow me to have a u value that will match the other part. And so this is a good candidate for long division or synthetic division. Okay, whenever your exponent is higher or the same as your denominator, you can go through long division or synthetic. I think we prefer synthetic, is a little bit faster. Okay, so the way you do synthetic, you take the opposite sign. So there's a +2 here. We're going to choose -2. That's what we get if we were to solve for x. Create a half box, and now we're just going to bring down the numbers. But we're starting with a degree 4, so we need to have a place for degree 4, a degree 3, a degree 2, 1, and then nothing. Okay. So degree 4 has a coefficient of 2. Notice that it skips degree 3, so we need to have a placeholder for it. So have a placeholder for it will be 0. Okay. Bree, can you figure out? Can you tell me the rest of the numbers that's going to go up top?
-1.
Okay. -1 for x squared. What's next?
And then 1.
Well, we have x to the 4th, right? This is for x cubed. This is for x squared. And what's below x squared?
X.
X, right? So we don't see any x here.
Mm-hmm. Would it be
there needs
0
to be
then?
yeah, there needs to be a 0 for x. And then we have a 1. Okay. All right, do you remember the process for synthetic, or do you want to try it, or want me to go over it?
Could we walk through it? Don't you
Yeah.
bring down the 2 and then
Yep, good.
multiply?
Yep, bring down the 2. What's next?
-2 times 2 equals
Good.
4. Or
-4,
oh my
right?
God.
Yeah. And then?
Doesn't equal -4.
Yep. All right, keep going.
And then equals +8.
Mm-hmm.
That'd be 7.
Mm-hmm.
And then -14.
Mm-hmm.
And -14. And then, oh my God, 28.
Mm-hmm.
And is that plus? Yeah, 29.
Yeah. Now we started with x to the 4th. Do you remember what we start with down here?
Is it x to the 3rd?
That's right. Yep. With synthetic, we always, because we're dividing by x to the 1st power, all these degrees are going to fall by 1. So yeah, x cubed. And so the next must be what?
X squared.
And then?
X.
And then?
That's just the coefficient.
Yeah, constant.
Yeah.
And then?
A constant.
Well, there's a name for this last term here.
Is it plus c?
It's the remainder. It's the leftover.
Oh, okay.
So the way we write the remainder is we put it over the divisor. So we have like this.
Okay.
Okay. Now we haven't finished the problem. but we've just made it easier for us to apply antiderivative rule. So now we're going to come to the side, write these terms out. And usually with synthetic division, what happens is your first few terms are just going to be power rule, but the last term is going to be a U-substitution natural log rule. That's usually the pattern that occurs. So what's power rule going to be for the first few terms? 2x cubed becomes what? Okay, so we add 1 to the exponent divided by that new exponent.
Oh, would it be
Oops,
2x? Oh, sorry, I'm late.
It's all good. You got it.
Okay. Oh no, I just lost my train of thought. Would it be 6x to the
Okay, so 6x, that
fourth?
will be derivative. Okay, that would be derivative. So let me start you off. So the first term, we're going to add 1 to the exponent, so it becomes 2x to the 4th over 4. So this is the opposite of power rule for derivatives. Okay, so see if you can do the next one.
4x cubed over 3.
Yeah. Okay, keep going.
7x squared over 2.
Okay.
And then 14. Would it be 14x over x?
No, just 14x, just 14x.
Okay.
Well, actually, it's 14x over 1, which is just 14x.
Okay.
Because right now this is x to the 0 power, and we're going to move it up from 0 to first power. Okay, good here.
Yeah.
Now this is a little bit of a U substitution, and it's the U value is this x plus 2. But eventually this, I think what we want to do is we want to be able to jump directly from here to here without having to go through a whole. This is a relatively simple U substitution problem. So if you see something like this in this form, what you can do is you can just pull the 29 out, and you know the U value is the x plus 2, and you'll just do that rule there. So it looks like this, plus 29 natural log absolute value of x plus 2 plus c. We know there's no messy coefficient. There's no variable that needs to cancel out. So a lot of times I like to tell students, if you can recognize this as a natural log rule, just jump directly to that part. Okay. Do you need me to show you the full step here, or do you guys see it?
I see it.
Okay. Okay. Yep. So here's the antiderivative. You can reduce these fractions if you like, but I'm not taking off points if students don't reduce. Okay. Number 3. Can we split these up? So I think I see students on as I was grading quizzes that students wanted to split this up into individual fractions. Make it like this. But we can't do this, okay? It looks like an easy way to kind of move forward, but you can only do that if there are 2 terms up top and only 1 term in the denominator, or multiple terms up top and 1 term in the denominator. So if the problem looked like this, then you can split this up. Okay. But because we don't have this form, we're kind of stuck in terms of being able to move things around. So this is going to be a U-substitution problem. Any idea what the U value could be here? You guys want to throw out a guess?
Would it be 3 minus 5e 3 to the x?
Yeah. So if we let the entire denominator be the U value, the hope is that the derivative will take care of the top, and we can move towards this 1 over U rule. Okay. All right, there's our U value. To find the derivative, we're going to be, that's a constant, right? But the second term, we're going to use the e to the U times U prime. Okay, Emily, can you try this one here?
Wait, so we're doing it with the same, like, e to the U.
Mm-hmm.
Okay.
Now we're moving to the, we got to do the derivative first, get all these substituted before we can do the antiderivative rule.
Okay. So is it e to the 3 minus 5e to the 3x times negative 15xe?
Okay,
How
so
am I doing it wrong?
so the 3 is going to go away. Okay, so 3 is a constant, and we're just going to follow this rule here. Okay, so the rule says if I have e to the u, it just becomes e to the u times u prime.
Okay, so would it be like like 3x as the u?
Yeah, that's right. 3x is the u.
Okay. So then it's just negative 5e to 3x times negative 15x?
Yes.
Or just times 3x?
Yeah, just times 3x. But eventually we can get that negative 5 and 3x to combine to be negative 15x.
Okay.
But for now, we're just kind of following the rule. The coefficient's going to stay, and then we just do e to the u times u. Oh, sorry, times 3, not 3x, times 3.
Okay.
So it looks like, yeah, it's just going to be negative 15 out front. Okay, does that make sense? E to the u times u prime.
Yeah.
Okay, so we can clean this up here. Okay, cross multiply. Okay, divide the negative 15 over. Okay, Bree, do you want to put this back in? See what that looks like?
Yeah, okay, so it'd be 2e to the 3x over 3 minus 5e to the 3x.
Okay, what can we do with this part that I underlined?
Oh, replace it with u. Okay, I was curious.
Yeah.
And then times du over negative 15e to the 3x, I think it was.
Yeah.
Yeah, 3x.
So what's nice about this from here on out? What works out?
You can cancel out the e to the 3x.
Okay, what can we push out?
The 2 or negative 2 over 15.
And now we got a perfect match, right?
Mm-hmm.
Okay, so what's the answer?
it'd be 1 over u du equals ln or would it be would it be the negative 2 over 15 equals ln absolute value u?
Yeah, no equal sign. We'll just jump directly into that natural log of u plus c.
Okay.
Yeah, so this piece gets replaced with that, and then the coefficient just hangs out in front.
Okay.
And then final step.
Plugging in u.
Mm-hmm. Yeah, I think the hardest part is getting started, right? Once we know where to start, the rest just kind of all procedural and everything kind of falls into place. Okay. All right, let's try this one here. Secant of x minus tangent of 3x. So this requires us to look at the rules. Do you see rules that match up? So we have a rule for secant, right? And we have a rule for tangent. So we just have to apply those. Okay, so secant, what's that going to be? Just natural log, absolute value of secant of u. And then because my u is just x, I just replace my u's and x. There's no need for u substitution. Well, we don't have to keep track of any leftover terms here. Okay, does that part make sense?
Yes.
Okay.
Yes.
Now the tangent, we got to be careful here. There's something left over. What's different about the tangent? Because we have a rule here, but there's something that we got to be.
Sorry. Is it because there's cosine with it?
No, there's something about the tangent that makes it a little more than what we saw with the secant.
Oh, is it the 3?
That 3x. Yeah, that 3x. That 3x tells us there's going to be something that is going to be in front. Okay. But let's just follow the rule here. Okay. We'll put natural log cosine of 3x. Okay. With the negative in front. But here is the way that we can do a little bit of a shortcut. Okay. What's the derivative of 3x?
3.
3. Okay. Now with derivative chain rule, we would just put a 3 out in front, right? Cosine of u times u prime. But with antiderivative, it's going to be still involving the derivative, but we got to flip it. It's going to be the reciprocal. So it'll be 1/3. Now we can go through U-substitution and show all that, but this is a bit of a shortcut. Okay, just understand that I got to keep track of my 3x. I know a 3 is going to be involved, but it's not the derivative, it's the antiderivative. So what's going to happen is we're kind of undoing the process, so we need a 1/3 instead. Okay, does that make sense?
Yes.
Okay, so to do another example, just to see if this all makes sense. What if I had the integral of cotangent of 2x over 3 dx? What do you think that would be?
Would it be 3 over 2x ln, and and then absolute value of sin. And that would be the 2x3.
Okay, you're close.
Would it be the derivative of
That's right. Yep. So 2/3 x becomes 2/3, and then you flip 3/2 and you lose the x.
okay.
So just the 3/2. Yeah. Now, if it's anything more complicated than that, if it's a higher degree, then I would go through U-substitution. But I feel like if it's a linear term, if it's x to the first power, we can save a few steps. Okay, number 5. This looks messy, but do you see how this matches with this rule here? So the idea is that we can see that this is the a value. This is an exponential function. This is 3 raised to the exponent. So if we can see that connection, then we can work towards that rule. So if we're trying to match this with this rule, then what's our u value? Do you guys see it?
Would the u be the equation in the exponent?
That's right. All this is the u value. So we're going to replace these two pieces, and the hope is that this will go away to the point where we can get this problem to look like this form. Okay, all right. You want to try this? So if my u value is x cubed minus 4x squared plus 2x, what's my du dx? All right, now we can move back to the derivative power rule here.
So you find the derivative of that?
Right, derivative.
It'd be 3x2 or 3x squared minus 8x plus 2.
Mm-hmm. And cross multiplying?
No. Oh, with that, okay, no.
Yeah, so this times this equals this, right? Okay,
Mm-hmm.
Divide the 3x squared to the other side. And we're going to put it back, okay? Okay, I underlined this, so I'm replacing that with u. All right. The hope is that we can cancel these things out, but there's not a perfect match yet. Is there something that we can do to make these two look more similar?
Find the least common denominator for both.
Kind of. Let's do something with this. What can I do with this to make this look a little bit different? Okay. What about factoring? Is there anything I can do in terms of factoring here?
Factor by 3.
Yeah, let's take out GCF, right? So if I take out a GCF of 3, what's left?
Um, 3x squared minus 8x plus 2.
And now we're in much better position, right?
Yeah, and then you cancel those out. Okay.
Okay, so almost there. We're still trying to match with this rule here. This A to the U, let me fold this up. I'll put this over here. Hey, that rule there. So how can I rearrange it to look like that? I'm pretty much there.
Would you like multiply the 3 that you factored in the 3?
Yeah, so that's what a lot of
the A.
students want to do. They want to multiply these two together, but why can we not do that?
Because it's in the denominator.
No, everything's in the numerator. Everything's in the numerator, but the problem is that this 3 is not really a 3. This is a 3 to the u, so this is an exponential function. That is not free to multiply with that 3. So we just have to keep them separate. So we'll push this out in front of the integral. And then we're just gonna, do you see a match now? So my base is 3. So A can represent base of any exponential function. Could be base 2, could be base 3, could be base 5. In this case, it's base 3. Okay, good so far?
Yes.
Okay, so now we can apply the rule, right? So Emily, what do you think, what would this look like if I were to apply this rule here?
So it'd be 1 over ln 3 to the u. Would it be plus 3 or just plus c?
C? Yeah, plus C.
Okay.
But is there anything that we're leaving out?
The 3 on the outside.
Yeah, that 3 needs to stay.
Okay.
So you
And
can
could
leave
you
like
move
this,
that?
or you can put a 3 over ln 3.
Okay.
But is this our final answer?
No, because you can plug in the u.
Yeah, replace the u. Okay. All right, one last one here. Natural log of x cubed over x. We can bring the x up, but we're kind of stuck, right? These are not in the same family of functions. We can divide these out. So we got to go through U-substitution. What's our u value, you think?
Would it be ln x?
Yeah, so if you're having trouble finding the u value, look inside the parentheses. Now, I know that not every problem is going to have a set of parentheses, but if there's a set of parentheses, you know that's that's a helpful thing to see. So yeah. Okay, what's the derivative of natural log of x? Okay, what's u prime over u?
Would it just be ln over ln x?
Now, what's the u value in my rule here?
Oh, in that rule, x.
Just the x, right?
Okay.
So what's u prime over u?
1 over x.
1 over x, right? So when you find the derivative of natural log, there's no natural log showing up. It's just that u value being affected.
Oh,
Okay, cross multiply. Okay, we're going to make our substitution, and we talked about how we do see bounds, but it's the last thing we do, right? We don't touch the bounds until the very end. All right, what does this look like here? After I substitute.
you plug in for the u and the dx.
Okay, what goes away nicely?
The x.
So now we're left with a power rule, right? So what's the integral of u to the third?
Would it be u to the 4th over 4
Mm-hmm.
and then du?
Well, notice that when we do u to the 4th over 4, the integral drops out, du drops out, and we have a plus c. But in this case, we're going to leave the plus c out because we know there's bounds involved, so there's no plus c. So all we have is that.
Okay.
Now, can I plug the bounds in here? What do you think? Because I'm ready for the bounds, but can the 3 and 2 be involved with this expression?
No,
Okay, and why is that? What's the
because
issue?
there's no spot for them to like be put in because there's no x.
Okay, good. Yeah, so either we convert the bounds in terms of u and then use this, or we bring this back in terms of x and then rely on the 3 and 2. And I think most students prefer bringing everything back in terms of x. So we'll bring this back in terms of x. And now we can work in the bounds. Okay, which gets plugged in first?
The top one, the 3.
Yeah, yeah. And we always put a minus sign afterwards, and then we work in the lower bounds. You don't have to simplify it. As soon as you get to this step, you can leave it alone. That's sufficient. Okay, hope that helps.
Yes, that helped. Thank you.
Yeah, that helps a lot. Thank you so much.
All right, good. Yeah, maybe I'll reach out to you guys again yeah, if we want to do any help session with the with differential equation that we've been doing. So, all right. See you guys in class.
Thank you. Bye.
Okay,
Thank
bye.
you. Have a good day.
Bye. Uh-huh.